Okay, everybody, so we're going to start with a tangent line problem. This is one of the main problems that gives us a motivation on why we studied limits and develops our theory of derivatives. So the tangent line problem is this: how can we find the slope of a line tangent to just any curve at a given point? Now, there are a number of ways around this, but I'm going to talk about the one by Pierre de Fermat. Fermat's method went kind of like this. He said, let's consider a function such as f of x equals 2x minus x squared. Let me highlight this here. This is our function right here. We've got 2x minus x squared. And the question for us is, what is the slope of the line tangent to f of x at the point 2, 0? Now, we could have picked any other point, but this is just a convenient point right here. So here we are at the point 2, 0. Why 2, 0? Well, this happens to be a nice x-intercept, and maybe we can estimate something. But the problem is we only have one point on the line, and to find the slope of a line, we need 2 points. Right? I mean, x, y, the slope formula goes m is equal to y2 minus y1 divided by x2 minus x1. And if we say we only have that point 2, 0, right? Well, we can call it x1, y1. Call it x1, y1. But the question is then, well, what do we do about that second point? So that's where we have to be a little creative in our approach. And Fermat was actually a pretty creative guy when it comes right down to it. So let's talk about what he did. He said, all right, let's consider a line that we can calculate. How about a secant line? Let's just pick some other point on the graph at 1, 1 to make the illustration clear. So we know this graph passes through the point 1, 1 and the point 2, 0. If you don't know how that's come about, you can go ahead and just verify those points by pausing the video and checking it out yourself. But all right, if we have this line, well, we know that the slope through these 2 points would be pretty easy then. We're going to take y2, which I'm going to call 1, minus 0, which is our y1 point. And I'm going to take yx2, which is 1, minus 2, which is our y point. And so our slope at this point is going to be 1 divided by negative 1. That is, our slope is negative 1. All right, easy enough, you say. So how does this help me get that secant? Well, he says, all right, if we could choose it at 1, 1, why couldn't we have chosen it somewhere closer, like, say, 1.5 or 1.75 or something close to that, right? By whatever x and y coordinate we pick right here, we could substitute it into our formula and figure it out. So he said, all right, let's make it look like this. Let's say that there's some point, just some unspecified distance h away from the point 2, 0. In other words, along the x-axis, we go h points away, right? So that we're at the point 2 plus h. Now, I'm playing fast and loose with the value h here, saying, well, let's say 2 plus h. Well, h could be a negative value if we wanted to make it to the left or the right. I'm making it to the left because that's sort of in between. All right. So at x equals 2 plus h, we might ask, what's the y value? Well, the y value will be f of 2 plus h. And then we would want to figure out what the slope is for our equation. So, okay, here's x2. Here's y2 now. So let's go ahead and substitute that into our formula, and our slope would look like this. Something like f of 2 plus h, whatever that turns out to be, minus 0 divided by 2 plus h, which is the x value, minus 2. We'd have to figure it out from there. Well, in fact, this is what we're actually looking at. We're actually looking at a formula that looks like this. F of 2 plus h minus f of 2 equals h. And what we really want to do is we want to see, well, what's going to happen if we let that point, that value of h get really, really small? Right, we want to let it get small. What does that mean? Well, small numbers, right? Numbers that are less than 1, I would suppose, or maybe 1/2, or however you define that. So let's see what happens in this case. Well, we know that f of 2 plus h is going to be the same thing as 2 times 2 plus h minus the quantity 2 plus h squared, whatever that works out to be. And we already know what f of 2 is. F of 2 is equal to 0 because we've already established that this graph passes through the point 2, 0. So if we make the substitutions right here, let's see, I'm going to simplify this f of 2 plus h business to give me 4 plus 2h minus the quantity 4 plus, let's see, if I take 2 plus h times itself is going to be 4h plus h squared. So combining all the right terms right here, 4 plus 2h minus 4 minus 4h minus h squared is going to go in here. Well, there's 4's, by the way. That should go. So our slope of our secant line is 2h minus 4h. So that's negative 2h minus h squared minus 0, all divided by h. And if we do our math correctly right here, let's see, we can factor out h from the numerator, negative h, pardon me, giving us 2 plus h divided by h. And as long as h is not equal to 0, then our quantity, negative 2 minus h, is our slope right there, right? So this is, let me erase that because that looks a little horrible. Let's try that again. Let's make it 2 minus h, negative 2 minus h. Okay, so this is the slope of our secant line as long as h is not equal to 0, but we actually kind of wanted to make it look like it had to equal 0. Well, luckily we have a tool in our tool chest to do this. We could say that the limit as h approaches 0 of the slope of that secant line would indeed be the slope of our tangent line. And that's what we want. What would be the slope of our tangent line here at this point? So let's take that limit as h approaches 0, because it doesn't really matter what happens at h equals 0. Remember that a value of a limit is independent from the value of the function at that point. And in this case, our function of h just approaches negative 2 by direct substitution. And so that's our slope right there. And that's how Fermat would have done it. Maybe a little bit of a different language, but there you go.